Let's code up an algorithm to do matrix-matrix addition. In order to add two matrices, we'll call them A and B, and we'll assume that they are an element of Rm by n. In other words, these two matrices have the same number of rows and columns. We say that the matrix sum A plus B is obtained by adding the individual entries of A and B. In other words, to get the entry in row I and column K of the sum A plus B, we take the sum AIK plus BIK, where AIK is the ikth entry of A and BIK is the ikth entry of B. Let's explore some different algorithms we can use to implement this operation. To do that, we'll start a new script file. We'll go ahead and save as. In this case, this is part of the BLOS level 2 discovery process. So we'll go ahead and call this matrix-matrix addition via rows is going to be the first one that we do. So now that we have that, of course, I should probably change this not just via rows, but actually this is a sandbox to remind myself that I'm just doing this for fun. Here, let's go ahead and save m to be the number of rows and then n to be the number of columns. We'll keep those small so we can actually get our head around what's happening here. Then what we'll do is we'll define A to be a matrix that has m rows and n columns, so m by n, each of whose entry is a random integer. And in this case, why don't we go from 1 to 20? And then the same thing for B. We'll reuse that line of code. B is similar structured matrix, so let's go ahead and write A, B. And then what we see is MATLAB already has a version of this, so we'll call this CMAT, which is MATLAB's native output. If I add A and B, the MATLAB's addition operator will do this for us. So CMAT is now our desired sum, given that we've now re-entered A and B appropriately. What we're going to do is try to create an algorithm to replicate this using for loops. So specifically, if we look over here, what we want to do is add the individual entries of A and B. There's kind of two different levels we can do this at. We can do this at the vector level, or we can do it as a scalar level. Let's start with a vector level, and then we'll drop down into the scalar level. In the vector level, to add the individual entries across a row or a column, all we do is just add the two rows or add the two columns. Let's start with the row perspective. So what we're going to do actually is run through the rows. So we're going to say from I goes from 1 to m. We'll go through all the rows. That the ith entry of the output, for now, let's go ahead and initialize this to be all zeros. So we'll say that this is zeros m by n. And then we'll say that the ith row of this matrix is going to be the ith row of A plus the ith row of B. So in this case, let me go ahead and save this. We want to check if the calculations we did align with the calculations that MATLAB does natively with the addition. So we'll go ahead and define an error to be the difference between the two of them. We say that when the error is 0, we've done really good work. Let's go ahead and run this to take a look at the error. Those two things are identical, which means we have a row partition version of matrix-matrix addition where we're forming each new row by adding the corresponding rows from the matrices that we want to sum together. Now, of course, in this particular algorithm, we've actually done some kind of silly work in terms of computer science. We're defining a brand new matrix C that's going to hold the sum, but we don't necessarily have to do that. Specifically, one of the really cool things about computer science is that we want to be cognizant of memory. What we could do instead actually is just overwrite A with the sum that we're looking for, meaning that we use the same memory locations to store the updated matrix, which means at the end of this, the matrix A would store the sum that we're looking for. The benefit of this is that we minimize memory cost. The drawback is that if we wanted to get back to our original matrix, we'd have to do operations again to subtract so that we could get A back. But perhaps those benefits outweigh the drawbacks. We're going to go ahead and do that in this case. When we run, we see that the error is 0. The reason that that's kind of useful is when we visualize the math operation A plus B, the sum of two matrices, We have now done this in row partition version, which means that we form each new row of the sum by taking the associated rows of the two matrices that we're adding together. In this case, we leverage our memory saving device where we overwrite the previous value of A with the new values that we desire. So when we do this algorithm, we initialize by storing two matrices in memory. Then we drop into our for loop. The first thing that we do is we take the first row of A, add it to the first row of B, and then store the results, overwrite the results in the first row of A. We move down to the second iteration in our loop. In this case, we had 2 by 3 vectors, so there are only 2 rows, which means we take the second row of A, add it to the second row of B, store the results in the second row of A. Then when we exit our loops, the matrix A now stores the exact sum that we want. You astute viewers at home might recognize that this is a BLAS level 2. In other words, we're doing our operations at the vector level. We could, of course, do them at the scalar level. So let's drop down into BLAS level 1 and get to the details. We'll go ahead and comment out the BLAS level 2 version. In this case, we're going to replace the inner sum with a for loop. Specifically, for the ith row, we're going to go over the column. So in this situation, we're going to go for k goes from 1 to n. And then, of course, we got to end that. And then we're going to say that the ikth entry of A is going to be the previous ikth entry of A summed with the ikth entry of B. And we'll suppress the output. Let's go ahead and run this, and we notice that the error that we get is 0. In other words, this algorithm produces the exact same thing that MATLAB does for the data that we started with. Let's visualize what we've just done. A math operation that we're doing is matrix addition. We have a doubly nested for loop, first running through the rows, then running through the columns. We would call this a row partition of the sum. In the body, we replace the ikth entry of A with the sum of that entry and the ikth entry of B. When we initialize this algorithm, we have two matrices sitting in memory. Then we drop into the for loop. So we set the first index equal to 1, the second index equal to 1. So we take the first entry of A, add it to the first entry of B, overwrite the value of that position in memory with that sum. Then we move along the first row. In other words, we increment the index on the inner loop. So we take the second entry of the first row of A, add it to the second entry of the first row of B, take the sum and store it in the second entry of A. Do that again to the third entry, which means we've gone completely across the first row. That means we increment our outer loop index, and we take the first entry of the second row of A plus the first entry of the second row of B, sum them together, stored in that 2, 1 of A. Do the same thing for the second entries and the third entries along that second row. In this case, we did a 2 by 3 example, which means we're done at this point, and A now holds the exact sum that we wanted. That leads me very nicely into the community challenge for this video. Instead of showing you how I would adapt these algorithms to do this via columns, I'm going to give that to you as a challenge. Specifically, over here, we saw that in order to take this math definition and implement it as an algorithm, we could do that at a row level or individual entries within the rows, which means we form the sum by moving across the rows. Challenge for you is, how would you adapt these algorithms to do a column version of this? So specifically, instead of updating the rows individually to take the sum of the two rows, how would you change this to update the columns to take the sum of the columns? And then once you have that algorithm, how would you replace the body with another for loop to move across the individual rows in each column so that you have a doubly nested loop? I leave that challenge to you. A second challenge, of course, is to develop your own visualization of what's happening in that algorithm and relate it back to previous work that we've done in other videos. I thank you so much for your attention. We're now ready to implement a rank 1 update of a matrix since we have the outer product and matrix addition operations, and that's exactly what we're going to do in the next video. I'll see you there.